So what if I told you that there's this technology that's been out in the wild for over a decade, used in commercial products, and it claims to do something that is, well, computationally impossible? Today, we're going to crack open a paper that finally pulls back the curtain on this incredible claim. Constant time O1 probabilistic inference. Okay, what in the world does that mean? Well, the paper's central claim, the big bombshell, is right there. In simple terms, it means the system can find any piece of information in a database in the exact same amount of time. It doesn't matter if that database has 10 records, a million, or a billion. The size, it just doesn't matter. But wait, it gets even crazier. It does all of this on classical hardware. We're not talking about some exotic, super-cooled quantum computer that fills a room. No, we're talking about the kind of computer that's probably sitting on your desk right now. And that is the kind of claim that makes computer scientists just stop what they're doing and pay very close attention. So, how is this even possible, right? That's the million-dollar question here. It sounds like it completely breaks some of the basic rules of how we think computers work. And you know what? That's exactly what we're going to dig into. Okay, so here's our game plan. First, we'll look at where this decade-old secret even came from. Then, we're going to get into the real nuts and bolts, the Toridion byte and something called binary quantum rounding. After that, we'll see how it went from a wild theory to actual tech, how it might solve some of AI's biggest headaches, and finally, we'll ask the big question, is this a whole new path for AI? All right, let's start at the beginning. Everything we're talking about comes from this paper by Scott D. Forshaw, published in October 2025. But here's the thing. This is not your typical research paper proposing a new idea. Nope. The stuff in here, it's been proprietary, closed source, and running in commercial software for over a decade. This isn't a proposal, it's a disclosure. A big one. Okay, so to really get how this all works, we've got to start at the very bottom, with its most fundamental piece. We're talking about a totally new way of thinking about and representing data. So here's the key idea you have to wrap your head around. A Toridion byte? It's not actually a number. It's a string of arguments, basically a set of instructions. The best way to think about it is like a super compressed recipe. This tiny 64-bit recipe has all the steps needed for an algorithm to perfectly bake a much, much larger 128-bit cake. It's not just compression, it's a blueprint. Now take a look at this. This diagram basically shows us the anatomy of that recipe we were just talking about. And yeah, I know, it looks pretty complex, because it is, but every single one of those little components has a super specific job to do in putting the original data back together. So let's break down some of the key parts. So let's stick with that cake recipe idea, because it really works. The primer, that's like your flour. It's the starting point, the foundation that everything else is built on. The limits, well, that's your baking pan. It sets the boundaries, right? The upper and lower bounds you're working within. Now, the inhibitor is a really cool part. It's like that pinch of salt you add to a sweet recipe. A little tweak that fine-tunes everything and gets you much closer to the final result, really fast. And then you've got your multipliers and remainder. Those are the super precise measurements that bring it all together to recreate the original cake perfectly. Okay, so if the Toridion byte is the recipe, then this next part, binary quantum rounding, or BQR for short, is kind of like the magical oven. It's the thing that bakes the cake instantly. And believe me, this is where things start to get, well, a little weird and really counterintuitive. The paper literally uses words like tunneling to describe what BQR does. See, in this system, numbers have to be what's called binary safe. All that means is that if you break a number down into blocks of 3 digits, each of those blocks has to be a value between 0 and 255. BQR is the mechanism that lets the algorithm just jump from one valid binary safe number to the very next one, completely leapfrogging all the millions of invalid numbers in between. It doesn't have to check them, it just tunnels right through. And this right here shows you just how different this math is. Normally, 255 plus 1 equals 256. Simple. But in the world of TQNN, 256 is an invalid number. It's binary unsafe. So when you add 1 to 000255, BQR doesn't go to 256. It jumps all the way to the next valid state, which is 0001,000. Think about an old car's odometer clicking over. It's just like that, but instead of one digit flipping, it's an entire block of numbers. That's the shortcut. So the process itself is actually pretty simple to grasp, but the implications are just huge. You do some math, and you get a result that's binary unsafe. It breaks the rules. Then you apply BQR, And it's like a giant magnet just instantly snaps that invalid number to the next valid one. There's no searching, no testing numbers one by one. It's an instant jump. And that's the whole secret to how it achieves that constant time O1 speed. Now, a system this wild didn't just pop up out of thin air. Not at all. It's actually the result of more than a decade of research that didn't even start with computers. It started with a really deep question about how the human brain works. And here's where you can see the breadcrumbs. It all started back in 2015 with a paper called The Third State. It asked a simple question: how can our finite brains hold what feels like an infinite number of memories? The paper proposed that it must be using some kind of quantum-like compression. Then, later that same year, another paper showed this idea in action with a neural network that could actually heal itself. Fast forward to today, and the 2025 TQNN paper is the final piece of the puzzle. It's the one that lays out the exact math to make all that theory work on the computers we use every day. And this quote, right here, from that original 2015 paper, it's basically the Rosetta Stone for this whole line of thinking. The brain is a finite phase space. In order to exceed the physical limits of its storage capacity, a scheme of compression must be used. You see, the entire TQNN system is an engineered answer to that biological question. How do you fit seemingly infinite data into a finite box? And the answer they landed on was a totally new kind of compression. So that brings us all the way to today. And you have to ask, why reveal this decade-old secret now? Well, it turns out that the very problem this tech was built to solve, inspired by the human brain, is now one of the absolute biggest crises facing modern AI. The paper is super clear about why they're releasing this. Let's be honest, training and running today's huge AI models uses an absolutely insane amount of energy. It's a problem that's quickly becoming unsustainable. TQN is basically being put on the table as a possible way out, a path to get to powerful AI without the ridiculous energy bill and environmental impact. And if this works as described, the potential applications are, well, they're completely transformative. A system with constant time memory could be the foundation we need for real, scalable, artificial general intelligence. The energy savings alone would be a total game changer. We already talked about its ability to self-repair, creating a kind of digital neuroplasticity. And its knack for connecting different pieces of information creates a powerful associative memory, which the author even suggests could be a stepping stone towards a more empathetic AI. So what's the takeaway from all this? I mean, where does this leave us? Could this actually be a brand new path forward for AI? I think the fundamental takeaway is this. For years, the answer in AI has been go bigger. Bigger models, more data, more power. TQNN suggests a completely different way. It says the answer isn't brute force, it's smarter algorithms. It's about simulating quantum-style efficiency on the computers we already have. It's a path that's directly inspired by the most elegant and efficient computer we know of, the human brain. It really makes you think, doesn't it? For decades, it's been a fundamental rule. Bigger data means slower search. This paper just walks up and says, nope. So if a cheat code this powerful has been hiding right under our noses, inspired by biology of all things, it really makes you wonder, what other fundamental rules are we just accepting as true? What other impossible problems are just waiting for a completely different way of looking at them?